Okay, last time we derived some formula, right? Equation that how we can figure out the velocity of a fluid passing through a pipeline by using heated tube, right? Like this one that we derived. Then we derive Bernoulli's equation. Then we derive how we can figure out the stagnation pressure and what is the stagnation pressure. Here is the definition of the stagnation pressure that we derive. Then we learn about the energy line. Energy grade line is this, both are same thing. Then we line hydraulic grade line, right? Then we try to show you the how heated tube work. Then we derive Bernoulli's equation and we show you different form of Bernoulli's equation. The same equation you can express in different form. And how we can express Bernoulli's equation in a single sentence that was we described, right? We learned in the last class. Now we learn we solve some problem. Okay. Problem one. Right over here is air is coming in a direction from the left side passing to the right side. And say this is a pipe. And there is opening right over here, and there is a heated tube. And in that heated tube, velocity will be 0, right? So if I take 2 points, say I'm taking 1 point right over here and 1 point right over here. Then you can apply Bernoulli's equation on these 2 points, right? And what they're saying the fluid is passing here is passing through a channel, and there is a static tab over here. That's an opening hole, pressure tab. And there is a heated tube, and with the heated tube and the static tab, there is a manometer tube. And in the manometer, they put mercury. And when air flow, deflection of the mercury is 30 millimeter. And you figure out the velocity of the fluid. How we can figure out this problem? We already derived it. Okay, you just need to know apply Bernoulli's equation at point 1 and 2. Then you make a line right over here along this line, and you consider that this point and this point pressure is same. How can you figure out pressure over here? You start from upper point, point 2. From here, you already come down right over here, like manometer. And how much will be pressure over here? Same thing, 0.1 right over here. I can think 0.1 is right over here. So from this point, we count this much. Then you get, if you think this is point A, this is point B, you say pressure A equal to pressure B. Then you figure out the velocity of the fluid. You see in the previous slide, we already described it. You see, what is the difference over here? We just make the tab at the top, right? Right now we're showing over here. They just put it over here. Instead, in the top, they put at the bottom. And instead, the heated tube going upward, they keep it downward direction, like this one. Then they just attach to it a tube, manometer tube. So same problem. It will be same formula, but there will be 2G A's, then there will be rho manometer divided by rho of fluid. That means rho air is come. That will be velocity of the air. Okay. right over here. PS minus P1, that will be rho M. That means manometric fluid. Right over here, there is no rho. Why? Because fluid in the P2 tube, if I attach a manometer, they have the same fluid, water coming. This gamma, this rho is density of the fluid passing through the pipeline. So this will be rho F. So in our case, rho manometer mean manometer inside they have mercury, rho of mercury. And rho fluid mean density of air. Okay. So we are not solving, you just solve by yourself. You see, we apply manometer, how can figure out the pressure at 0.1 and 0.2. Similarly, you just figure out the pressure right over here and right over here by the manometer. Okay. Now we'll solve this problem by applying Bernoulli-Séguéchon. So what is the problem? It's saying air flow steadily at low speed through a horizontal nozzle. The nozzle is horizontal. Air is coming from the left side at a certain speed and pressure and getting out through the outlet from section 2. Section 2 has a cross-sectional area less than the section 1. So what will happen? You see, we know the continuity equation, right? That Q equal to A1 V1 equal to A2 V2. So from here, we can figure out the V2 from that equation. V2 will be A1 divided by A2, right? Into V1. Now this ratio, A1 by A2, always more than 1, right? Because A1 is bigger, A2 is smaller. So what happens? If area is reduced somewhere, velocity increase, right? So this kind of nozzle, normally they use in that to spray something, body spray, you spray aerosol, also the law enforcement agencies, then firefighter people, they use the water nozzle. So if we have higher velocity of water right over here, you can release the water, send the water at the far away in the second floor or third floor, right? So they are saying that area of nozzle at the inlet 0.1 meters square, already given over here, at the exit 0.02. Determine gas pressure required at the nozzle inlet to produce outlet speed 50 meters per second. So how much will be pressure if I say this nozzle attached with a tank? Then what will be the pressure need to maintain to have the velocity 50 meters per second? This kind of designing of nozzle. So how will you figure out? You need to apply Bernoulli-Séguéchon between 0.1 and 2. So if you apply 0.1, you get P1 by gamma plus V1 square by 2Z plus Z1. This is at 0.1. Energy at 0.1 will be equal to energy at 0.2. That means P2 by gamma V2 square by 2Z plus Z2, right? Now you see both are horizontal. So if anywhere you take the reference line, the height will be same. So Z1, Z2 will be out. Now you see the pressure at 0.2, atmospheric pressure. If you figure out the gas pressure, you can assume that atmospheric pressure is equal to 0. V2 is given 50 meters per second. You need to figure out the P1. So how will figure out the P1? You need to figure out the P1. If you want the V1, then you can figure out the P1 easily. Okay. So let's see. 1 second. Let me stop the sharing. I'm not able to see my MathCAD file over here. Okay. Now, did you see the MathCAD file?
Yes, sir.
You can see it? Yes or no?
Yes, sir.
You can see it. Okay. So here is the problem, and we'll solve it. Very easy. Let's see. So it's a area at the inlet, 1 to 1. So I'm saying given area at inlet of nozzle A1 equal to this one. Then area at outlet A2 equal to this one. Okay. Velocity at outlet of nozzle right at point 2, 50 meter per second, right over here. Okay. Then obviously you need the rho because you need to figure out P by gamma. P by gamma, right? So gamma equal to rho G. So you need to know what is the density of the air. It is not given in the problem. So in all case, you need to know two data. Density of the air, and also you need to remember density of the water. Then absolute viscosity of air, you need to know. Okay. Then you need to know absolute viscosity of water. Those data normally we don't give in the problem. Other thing to remember, density of mercury, 13,000 I think kg per meter cube. That you need to know. Okay. So the density of the air is not given in the problem. So you need to memorize. So you put this is the density of the air at normal temperature and pressure. Value of G we needed. Why? You need to figure out P by gamma. And gamma equal to, we know that gamma equal to rho G, right? So that's why you need to have value of G. So this is value of G. Now, if I copy this figure, right over here. Now, atmospheric pressure. We are thinking that atmospheric pressure equals 0 because we'll figure out the gas pressure. Now, what need to figure out? Pressure at inlet P1 equal to how much? That we need to figure out. Pressure at point 2 equal to P atmospheric pressure. Now, we'll apply Bernoulli's equation between 2 points. So this is Bernoulli's equation. Now, Z1, Z2 is same. That means this term will be out, right? Then we assume that P2 is almost 0 because atmospheric pressure. You can keep it P2, but then you need to put the atmospheric pressure. If you put P2 atmospheric pressure equal to 14.7 psi, right? Like 1.01 kilopascals. If you put that one right over here, P2, then your pressure will be in absolute pressure. So Z1 equal to Z2, then you have this formula. We need to figure out the P1. So P1 by gamma equal to P2 by gamma, this term, V2 and P2 left side, and write this on taken the right side. Okay. Now V2 we know. V2 is already given. A2 given, A1 given. V1 is not unknown, but we can figure out the V1 because we know the continuity equation that Q equal to A1 into V1 equal to A dot 2 A2 into V2. So A2 V2 we know, A1 we know, so we can figure out from here V1. Right over here we use this formula. Okay. So your V1 is coming A2 into V2 divided by A1. So this is my V1. It's coming 10 meters per second. Now we figure out the gamma because P1 by gamma. We need to figure out the gamma. So gamma equal to coming this mass 11.8 Newton per meter cube. So you have the gamma. Now all the value you put over here in the application. So P1 will be this value into gamma, right? That I put over here. And it's coming this mass below Pascal. And if you want, you can figure out the value in kilopascal. I just send the unit. And it's showing automatically in kilopascal. Okay. If I send the data, example, V2 of this problem, say V2, I am making 200 meters per second. Then you will see the pressure will be automatically sensed. Okay. Any questions so far?
Sir, why atmospheric pressure is 0?
Atmospheric pressure is not 0. You can keep it atmospheric pressure in the problem. Okay. So what is coming? You say if I say P1 equal to, you multiply with the gamma. So it's coming P2 plus you will have gamma into gamma star this value, right? You have this value. Now, what we did? We did P2 was equal to P atmospheric pressure. We can put the value. We assume that P2 P atmosphere equal to 0. Now, after calculate, you get some value over here. For example, you are getting right over here 110 kilopascals. So then, what will be the P2? You remember what is the absolute pressure? Absolute pressure equal to P gas pressure plus atmospheric pressure. Okay. Gas pressure means you are getting reading from the pressure gas or manometer. Then you add the atmospheric pressure, you get the absolute pressure. Now, in our problem, what they want? Figure out the gas pressure. Okay. So, what is the gas pressure hour? Gas pressure means you will not add the atmospheric pressure with the result. So, this was our gas pressure, that is 110 kilopascal, and this was our atmospheric pressure. So, we ignore the atmospheric pressure. Okay.
Okay,
Any
sir.
problem? If you ignore the atmospheric pressure, then your result in T1, right now I can say T1 equal to this much value, 1.10 kilopascal, but I have to say this is gas pressure. You cannot say this is the absolute pressure, okay? But if you add atmospheric pressure with this result, then you have to say mention in the bracket, this is absolute pressure, okay?
Okay, sir.
Okay, let's now solve the second problem. Let me share. One second. You see the PowerPoint.
Yes, sir.
You can see, right? Okay. This is problem 3. Problem 3 is saying water is flowing from a garden hose, that in plastic hose. A side placed thumb to cover most of the hose outlet, causing a thin jet of high-speed water to emerge. The pressure in the hose just upstream of his thumb is 400 kilopascal. If the hose held upward, what is the maximum height the jet would achieve? Sometimes what we do, say you are putting some water in the garden. So you have garden hose at certain diameter, right? So water is coming through the hose and getting out. So sometimes if you cover up some portion, then what will happen? You can take the water a little bit far away because area reducing, right? So velocity will increase, water will go a little bit far. So now if you hold the water upward direction, that's saying that how far water will be travel. So if he's holding this plastic hose, in cover up some portion. This is the cross section is showing over here. So this is the diameter of the tube or hose, and he cover up some portion, right? This much portion cover up with the thumb, and this narrow region water is coming out with high speed, and it's saying just upstream of his thumb pressure is 400 kilopascal. Right over here, pressure is 400 kilopascal. Now saying that how far water will travel in upward direction. So in upward direction, water is get out from the tube with a certain velocity, right? Velocity might be, it's a 100. So it will lead to the sky? No. Why? Because gravitational force pulling him down. So gradually he moving upward, but at one stage his velocity will be 0, right? If you remember the formula, the final velocity v square equal to u square minus 2 g right? So gradually u is moving upward due to acceleration working downward until this v becoming 0, then it moving upward, right? So at upward direction, when it is at the maximum height, then what will the velocity at that height? Obviously 0. Right over here, velocity becomes 0. That's why due to the gravitational force, water is falling down. Okay. So if we apply Bernoulli's equation between this point and this point 2, then we can figure out this height. How? Say this is our reference line. So at point 2, how much the pressure at point 2? Obviously, pressure is atmospheric pressure, right? So we can say P2 by gamma. What is the velocity at point 2? V square by 2g. At point 2, velocity 0. So we can say V0. Plus, what would be the height, Z, from the reference? Say Z2. That will be the value of Z2 we need to figure out. Minus P1 by gamma. P1 by gamma, P1 is given. Is saying right over here, pressure is 400 kilo Pascal, right over here. Then what is the V, V1? Just below the thumb, fluid is stop. Fluid velocity right over here, but over here velocity is 0. So we have V1 square by 2g, that means 0. And what is the height, Z1? This is reference line, Z1, 0. So P1 is given. So easily we can figure out the height, Z2. What is the value of P2? Atmospheric pressure. Okay. But you can say you are figuring out the height with respect to the gas pressure, then you can say this pressure equal to 0. So I say you can do it by yourself. At V2.2, V equal to 0, P2 equal to P atmosphere equal to 0. Z2 you need to figure out. So Z2 equal to what? Then P1 is given. P1 4000 kilopascal multiplied by 1000, V1 0, Z1 0. Easily figure out the Z2. So this is a simple example that how you can use the Bernoulli's equation in real life or to solve some real problem. Okay. Now let's see we can solve the problem 4. And how long our class? Until 2:40. That still we have time. Okay. And in the last class, I told you that the Bernoulli's equation didn't count one thing. Which one? The frictional loss. But sometimes you can use the Bernoulli's equation without frictional loss. That your error should not be that much. That means you can apply P1 by gamma, V1 square by 2g plus Z1, right? Then you put V2, P2 by gamma, V2 square by 2g, then there will be hydraulic loss or frictional loss. Okay. This loss Bernoulli did not count, but we'll figure out how we can figure out this frictional loss. But you see, we solved 2 problems. Like this one. The air or water is releasing in the atmosphere, so there is not that much frictional loss. Only there will be frictional loss due to the collision with the air and the water particle at the site, right? Because water is following upward direction and he has to move through the air. So the air has certain viscosity, but this will be minimal. So we can ignore that frictional loss. Similarly, in this problem, you see the distance between 2 points, point 1 and point 2, is not that much. Say using your body spray, using aerosol. The length of the nozzle is very small. So frictional loss between point 1 and 2 in that case is negligible. Okay. So that's why we already mentioned the Bernoulli equation, though for simplification, he didn't count the frictional loss, but still it is a powerful tool or equation. So similarly, we will apply Bernoulli's equation in problem 4, and you will see we will not count the frictional losses. So it's saying water flowing under a sluice gate on a horizontal bed. At inlet to a flow means like creek but canal. Okay. Upstream from the gate, water depth is 0.46 meter. That means at this gate, depth of water is this much. And this depth is constantly maintained because water is coming through this side. And if the gate is closed, then what will happen? The water is gradually, water height will increase. But you release the gate and normally we maintain the constant height. Like we have a hydraulic power plant in Kaplai. They have a dam in the river, so they always maintain the constant height. Why? Because energy of the fluid right over here, what kind of energy we have? You see right over here, what kind of energy? This fluid, if you maintain the constant height, there is no velocity. Only you have the pressure height. How much the pressure will be over here? H rho G. Height increasing, pressure increasing. So if this height you are not able to maintain constant, then what will happen? The pressure energy, water is coming out through the bottom portion, the pressure change, then this velocity V2 will fluctuate. So your turbine blade will not rotate at constant speed. It will be fluctuate time to time. So that's why in hydraulic power plant, always they maintain the constant height. Okay. Now, in some case that you have water is coming, especially in the summer or rainy season, too much water coming, and you are not able to maintain constant height. You open the full gate, still your height is increasing. Then what you can do? In that case, you just release some water, like Farakka barrage. What they do? Still they need water, so they close all the gate. Then it's an water rising too much. Then they open some of the gate, right? So same thing over here. So it's saying what I'm like to mention, the right over here, fluid velocity 0 and maintain constant height. So in the problem, this one what they're saying at the upstream height is 0.46. And already they are mentioning over here. Even don't mention, but still you can assume that velocity of the fluid at the upstream, but at 0.2 right over here is 0. At the Vanna contractor, I will explain what is the Vanna contractor. This is one term of fluid mechanics. Downstream from the gate, the flow streamline are straight. That means from the downstream, water is coming out at a constant speed and is straight. Okay, and depth is 0.051 right over here. This much depth from here to here is 0.051 meter. Determine the flow speed at the downstream. That right over here, we need to figure out the velocity of the water. And also discharge in cubic meter per second per meter width, or they can only say figure out the discharge. Discharge means how much water is flowing per unit time. That in Q will be meter cube per second. So if you know the velocity and you multiply the area, easily you can figure out the Q. Okay. Now what we'll do, we'll apply Bernoulli's equation right at the top surface right over here, and we'll apply Bernoulli's equation right over here at 0.2. So you see at 0.2 right over here, velocity 0. What is the pressure? Atmospheric pressure, right? But if this is the reference line, this one is reference line, then what will be the Z1, 0.46? What about the 0.2? How much the pressure right over here? Yeah, right over here, right over here, even right over here. How much the pressure? Atmospheric pressure, right? And right over here, you apply Bernoulli's equation. What will be the height? Z2. Z2 will be 0.0. 5. So from there, easily you can figure out the velocity V2. If you have velocity V2, then you multiply the area of the gate. Then you will get the Q. Okay. Now, what is Vana contractor? This term. If you look carefully, say you are taking shower in the washroom, and if you look, you open the full gate of your tap. Say this is your mouth of your water tap, and you open full gate. When you see water is coming out, right? And you see some portion, you will see diameter of the water little bit shrink when it's falling down. You can look carefully. So right over here, the water streamline is shrink. That region is called Vana contractor. Okay. So right over here in this gate, water is getting out. Then you see water could flow directly in this direction, right? But no, water is flowing coming downward. Then he might go straight like that, or after that might go upward. Okay. So right over here, the shrink is 0.2 at the Vana contractor. Now, how we can solve this problem? Very simple. And one thing that width of the, this is the gate we are looking in the side view. Actually, what happens if you like to make in 3D view, and this gate, you can move up or downward to close it. Okay. So if I make it clear view little bit, so I'm saying this might be say 200 feet or 300 feet wide, right? Depends on the where is it. It might be on the canal or might be a river, right? So you see water is coming out through which area? This area, right? This area water is coming out. So you see, if you know the V and multiply this much area, then you get the Q. Now, right over here, what is this height? That means height, this much height. The height is given, Z2. So area, this W is not given. So what will be the Q? Q will be, if you figure out the V2, then multiply by area. Area A2. So what is the area? This W into this height. So this height is 0.051. So Q equal to V2 into W into Z2. Okay. Now W is not given. Then how we can figure out the Q? So you just figure out Q by W. That means how much water is flowing if width of the gate is 1 meter. This way we figure out the flow rate. So let's solve it. One second, stop sharing. Okay, did you see the math card file? You can see?
Yes, sir.
Okay. So let's do this one. So it's very easy. You apply Bernoulli's equation between 2 points. That means you take right over here and right over here. Okay. So atmospheric pressure, I'm assuming right over here is 0. So P2 is atmospheric pressure, P1 also atmospheric pressure. Even if not considering 0, still P both will be out, right? V1 is 0. Z1 is given that much. P2 is atmospheric pressure. V2 you need to figure out, and Z2 is given. So if this one comes in the exam, you draw the figure, you say answer to the question number 2 or 3, then you figure out the what data is given. P1 equal to atmospheric pressure, P2 atmospheric pressure, Z1 is 0.46. Before you say 1 and 2, you need to mention where is the point 1, where is the you're considering point 2. And also you need to show that which point is the reference line, like you considering this one is the reference line. Then V1 at point 1, obviously 0. Z2 0.051. Then rho you need to figure out. Rho is 100,000 kg per meter cube. And then figure out the gamma, Z value this much, you get gamma. Okay, now all the value you put over here. So P1, we are assuming atmospheric pressure equal to 0. So P1 0, V1 0, this is Z1, gamma P2 0, V2 Z2. So from here, Z1 we know, Z2 know, you can figure out easily V2. So you figure out the V2 from here. You get V2 equal to this meter per second. Now, how will get the Q? V2 into area. So Q equal to, we are saying W into H into V2, velocity. Now H will be equal to Z2. So what will be Q by W? Q by W will be V H into V2. That will equal H into V2, and this H equal to Z2. So Q by W, that I mentioned the small QW, that means flow rate per unit width of the gate. So Z2 into V2. Finally, you are getting this result. Okay. You see this unit Z2 into V2. What is the Z2? Meter, right? Unit of Z2 is coming meter. Into what is the V2? V2 is coming meter per second, right? Now, then how we figure out the unit? Q is meter cube per second. You need to figure out this unit, meter cube per second per meter. So what you can do, you see, if you match the unit, you are getting meter square, right, by second. Then you multiply both sides by meter. Then at the top, you are getting meter cube. Then second, I'm to the bottom of this one. Okay. Then this meter, I'm giving right over here. So same thing. So ultimately, you multiply velocity by height, then you are getting flow rate per unit time per unit width of the gate. So this is the answer. Okay. So far, any questions? Anyone? Any questions? No. Anyone?
No, sir.
No, sir. Okay.
No, sir.
So we can stop it here, right? Okay. So thank you very much. Stay careful. Okay. Bye.